All right. Good afternoon, everybody. So a couple of reminders before we get to talking about synchronization is that our last quiz is coming up next week on Thursday. It's actually in the same rooms as quiz 1 was, so it's 2 different rooms. So on our website, we have the exact details of who should go where, but basically you should go to the same room you went to for quiz 1. Second thing is the quiz review was going to be again on Tuesday at 7:30, also in the same room. And if you have a conflict with the quiz, make sure to send us a private Piazza post as soon as you can so we can get you scheduled for a makeup. Thank you. Give me a second. All right. Terrific. All right, so today's topic is synchronization. So we've been talking recently about, what kinds of things we can do in order to improve the performance of our processor. So something that we definitely want to consider is to do things in parallel. And so what I mean by that is, let's say that I have a computation and I can divide it up into multiple sections, which we'll call threads. What I want to be able to do is execute these threads in parallel. Now, these threads can be related to each other in one of 2 ways. Either they can be completely independent, so each of the computations has nothing to do with the other, so they can just run in parallel, but there, what I have to worry about is shared resources. So if I'm running on a single processor, for example, I have to share the CPU, I have to share the memory, I have to share I/O devices, and so I have to figure out how to allow the different threads to share these resources. Another alternative is to have multiple cooperating threads. So the idea here is that the threads are actually communicating with each other and sending data back and forth. So in this case, not only do I need to worry about shared resources, but I also need to make sure that processes only run when they have the data that they have available to them. And I have to think about, how are we actually going to share this information from one processor to the next. So there's 2 communication models that we think about. The first is a shared memory model. And the way this works is you basically have a single address space, and these little gray things are your individual threads. And whenever they want to communicate with another thread, what they do is they write to a particular location in memory, and then the other thread is going to go and read from that location in memory, and that's how they communicate with each other. An alternative to shared memory is what we call message passing. So in a message passing model, each of the processes would have its own address space, and so the threads run independently of each other. And when they want to communicate with each other, what they do is they actually send messages which are transmitted over this shared network in order to communicate with one of the other threads. So we're mostly going to be focusing on shared memory in today's lecture, but it's important to know that both are certainly very common ways of doing this. All right, so once we talk about doing things in parallel, then we also have to start worrying about synchronization. So what do I mean by that? If you have multiple threads that are in some way related to each other, then it might be, you might want to do something like what's shown over here, where I, at some point, fork off and do 2 things in parallel, where process 1 is doing part of my computation, process 2 is doing another part of the computation, but before I can move on beyond that, I have to actually somehow merge the 2 results that both of those threads produced, and then continue from there. And so we have to have a way of being able to fork processes and then join them back together. Another situation we need to deal with is a producer-consumer relationship. So the idea here is you might have one process that's producing, data for the consumer to consume, and then the other process that's trying to consume it and do something with it. Of course, the consumer can't run unless the producer produced something. So again, we have to have a means of synchronizing the communication between the two of them. And finally, there's also what we call mutual exclusion, where you have a single resource or a limited number of resources that have to be shared amongst multiple processes. And so what we do in this case is we have the operating system be responsible for determining which one of the processes gets to use that limited resource at any particular point in time. And so once again, we're going to do this through synchronization. All right, so what does it mean to have a thread-safe program? So first we're going to think about it in terms of running it on a single program, on a single processor. So we already know that we can run multiple things on a single processor by doing time sharing, where our operating system is going to have some kind of a timer that goes off, and it's going to allot a fixed time period for for process 1, then another time period for process 2, and so on. And so you could imagine that if you took your computation and divided it up into multiple threads on a single processor, you could run it in exactly the same way, where the operating system switches from one thread to another, and it does this in a round-robin fashion, and they all make progress. Now, if you were to run multiple threads on multiple processes, then the question becomes, what is the correct behavior? So we define the correct behavior of a thread-safe program to be one where the result is exactly the same if I'm running it on multiple processors than if I was running it on a single processor. And so then, just to make things simpler and not have to worry about the operating system and time sharing and all of this, we're going to assume for the rest of today's lecture that each of the threads is actually running on its own processor. Okay, so let's start looking into what kind of problems come about when I have these multiple processes running in parallel. So the first example we're going to look at is this producer-consumer model. And what I have here is two simple pieces of code. The producer loops through its piece of code over and over again, and what it's doing is some instructions, we'll call them XXX, and then that produces some output which it's going to send to the consumer, and then it goes back and it repeats this over and over again. The consumer, on the other side, is waiting to receive some value from the producer, and then once it receives it, it does some operations, we'll call those YYY with them, and then it's going to repeat its process. So in terms of what's happening over time, the producer, takes its first iteration through the loop, runs the instructions XXX, produces a value and sends it. Then it's going to produce the second value and send that, and so on. The consumer, on the other side, is going to, receive a value, do something with it, then receive another value, and so on and so forth. So because these processes depend on each other, what we need to add to this picture is what we call precedence constraints. Okay, so I have to have a way of saying this little sort of curly less than sign means that there is a precedence constraint where A must precede B. Okay, and so if I look at this example of the producer and consumer, what has to be true in order for this to work properly? Can they just execute in parallel without any synchronization between them? Yep.
The producer needs to set off some information before the consumer can.
Exactly, right? So my send one must come before my receive one. My send two must come before my receive two, and so on. Okay? So basically what we're saying is that send of I must precede receive of I. Are there any other constraints that we have to be concerned about here? Any ideas? Yeah?
Maybe ensure that you receive one before you receive two.
That's exactly right, because if, let's say, the way that I'm communicating between these processes is that I'm writing my character or my value C to some shared memory location, right? I want to make sure that my consumer consumed my first element before I overwrite it with a new element, right? And so the second constraint here is that receive of I should happen before send of I plus 1. Okay, at least in this simple model where the communication is just through one location in memory. Okay, any questions about that? Great. All right, so we'd like to, deal with these precedence constraints, but also potentially relax them a little bit. Okay, so one thing that we can do in order to relax some of the constraints is to, instead of using just a single fixed location in memory to do the communication, we could actually insert a FIFO between our producer and consumer. And so if my FIFO is an n-element FIFO, then that allows the producer to get up to n steps ahead of the consumer. Okay, and so basically the way that we express that in terms of precedence constraints is that receive of I must precede send of I plus n. So how do we implement this? The typical way of implementing this is using what's called a token ring, which is basically the same as what you saw in your Italian kitchen problem that we solved in lab. And so let's say here that I have, a 3-element buffer. What I would do is I would have 2 pointers to it. One, which is the location from where the consumer is going to read values, and the other is where the producer is going to write values. And so in order to satisfy my precedence constraints, the first thing that has to happen is that I have to write something into this buffer. Okay, so I come in here, I write element C0, and that goes into the first location of my buffer. And now my write pointer moves to the second element of the buffer. Okay, now at this point, either a read or a write can happen. And in this particular example, let's say, another send happens. And so I put a second element in my buffer. And now, once again, either can happen. And let's say I put a third element in my buffer. Now at this point, my buffer is full. Okay, so I cannot continue to send elements until at least one receive happens. Okay, so the next thing that I'm going to see is that my consumer receives one character, and then we go on in this way. Let's say we get another character, and you see that my read pointer is moving over one element to the right every time I read, and my write pointer is moving over one element every time that I write something. And so, and then once I finish with the last element, I just wrap back around to the beginning. Okay? So our goal is to use shared memory in order to try to implement this this buffer, this ring buffer that we just described. So let's start off and let's assume, that I'm defining a buffer of size n in my shared memory. We'll call that buff of n, and it can hold up to n characters. And I have 2 pointers, in and out, which are used in order to be the pointer for in is the pointer for the producer, where it's going to put things into the buffer, and out is the pointer for the consumer, where it's going to take things out of the buffer. And so now you can imagine that, the code for sending and receiving is fairly simple. So it would look something like this. The producer has a character that it wants to send, so it puts it into buffer at the location in, and then it increments in by 1, and we have this modulo n so that it wraps back around to location 0 once it falls off the end of the buffer. Okay? Similarly, the consumer is going to read from the buffer at location out, and then it's going to increment the out pointer by 1, again, mod n. Okay? So, looks pretty simple, right? But is this going to work? What do we think? I think it's not going to work. Can anyone tell me what's not going to work about it? Yeah.
I think we need to like check out if we put down like if we're overwriting something.
We need to check if we're overwriting, and we also need to make sure that we don't consume something before we produce it, right? So let's see, how we might go about fixing this problem, okay? So the first problem we're going to try to fix is, how do I make sure that I don't consume something before my producer actually produced it? So what we're going to do in order to deal with that is we're going to use a new data construct, which is called the Semaphore. This was invented back in the 1960s, and basically the way semaphores work is as follows. A semaphore is essentially an integer, which is set to a value that's greater than or equal to 0. And when we declare a semaphore, we initialize it to some value. And then there's two types of instructions that deal with semaphores. The first instruction is a wait instruction. So if we say wait on a semaphore, what that does is that basically stops you from executing the instructions that come after this wait until you get a value of the semaphore that's greater than 0. Okay, so if the semaphore is greater than 0, then your wait will succeed, meaning you can execute the instructions that follow it. And when it succeeds, it's going to immediately decrement the value of the semaphore to be s minus whatever the value was, minus 1. Okay? The other instruction that we use with semaphores is signaling of a semaphore. And so when you signal a semaphore, you're incrementing the value of that semaphore by 1. And so basically, the kind of semantic guarantee that we have is that if you initialize your semaphore to k, then it must be the case that you can't get k, more than k ahead of your wait. So in other words, if let's say I initialized k to 2, it would be possible for 2 waits to succeed before I sent any signals, but not more than that. Okay, so let's see how we can actually make use of this in order to try to solve the buffer problem that we had. But before we do that, let's first see, how do we even use semaphores in order to establish a precedence constraint? Okay, so let's assume here that, I have these two threads that have, pieces of code, A1 through A5 and B1 through B5. And let's say that I want to make sure that the piece of code A2 runs before B4. Okay, so how would I go about doing that using semaphores? Well, what I would do is I would declare a semaphore and I would initialize it to the value 0. Okay, then at the beginning of my arrow, which basically is right after A2 executed, I would put a signal of that semaphore, and on the other end of the arrow, I would put a wait of that semaphore. Okay, so by doing this, what have I achieved? I've made sure that the code in B4 cannot run until after the code of A2 completes. Does everybody see that? Okay, great. All right, so in addition to using semaphores for precedence constraints, we can also use it for resource allocation. So imagine that you're in some department store and it has 3 changing rooms, okay? And there's a whole bunch of people who want to use this changing room. So what I want to do is I'm going to declare this, semaphore with an initial value of 3. And as people request a changing room, my value of my semaphore is going to decrement until all 3 changing rooms are full. At that point, of course, I can't assign any more changing rooms until somebody's done. Okay, so once someone's done, they're going to come out of the changing room, they're going to signal it, and so once again, I have a changing room or a resource available to give to another consumer. So basically, how did that work? What we did is we declared a semaphore, we initialized it to the value k, which is the number of that, how many of that resource you have, and then the way that each user would use it is that before they begin to do anything, they have to wait for that resource, so they wait for that semaphore, then they do something, and then when they're done with it, they signal the semaphore, okay? All right, so let's go back to our code now and see how we're going to use these semaphores in order to deal with these precedence constraints, okay? So what we're going to do is we're going to declare a semaphore. We're going to call it characters, and we're going to initialize it to 0 to indicate that initially I haven't produced any characters, okay? So now my producer, after it produces a character, it's going to say signal character. So my character's semaphore is going to get incremented by 1, and my consumer over here, before it does anything, it's going to wait for characters. So initially characters was 0, which means that the wait just stalls and you can't get past it, right? As soon as the producer produced something and made my characters be 1, now my consumer can go ahead and execute, okay? So in that way, we're making sure that we don't consume things that weren't yet produced. So this, takes care of the precedence constraint of send I must precede receive I. And in addition, it also helps us keep track of our resources in the sense that the value of the semaphore, of the character's semaphore, tells you how many characters you currently have available to be consumed. But have we dealt with all of the constraints? We had another constraint that we had to deal with, right? And what was that? It's not enough to just not consume before I produce, but what else does the producer have to worry about? In the case where we had a single location in memory, we said the producer can't write to it until the consumer has read from it, right? Now, even if I have an n-element buffer, I still have the same problem, which is I can't overflow my buffer, okay? So my producer can only get up to n ahead of my consumer. So in order to do that, I need to declare yet another semaphore. So a new semaphore that I'm going to declare is, let's call it a spaces semaphore. And this semaphore is initialized to n because it's trying to indicate how much space is left in my buffer, not how many characters have I produced. So initially I have n spaces left in my buffer. And so for the producer to be allowed to run, it needs to first make sure that there's space in my buffer. So the first thing the producer does is it waits for space. If there's space, then it decrements the space semaphore value by 1. It does its work of putting something into that buffer, and then it signals character to indicate to the consumer, hey, now you have a character ready to consume. The consumer, on the other side, first waits for characters to be available before trying to consume anything. And when it's done, it signals space to indicate that it just freed up a space in the buffer. So if the buffer was full, the signaling of space allows the producer to now produce one more element. Okay? So this looks pretty good, right? We're almost there. It actually turns out that this only works if we have a single producer and consumer. And later in today's lecture, we're going to see what exactly goes wrong if we have multiple of them. Okay? So we're making progress. So now let's take a look at another type of issue that we might need to use synchronization for, and that is simultaneous transactions. So suppose that I have a bank account and I want to take $50 out of it, and my friend wants to take $50 out of it, okay? The correct behavior would be that the balance of the account when we're both done taking $50 out of it is that it's 100 less than it was initially, right? So suppose that my bank account has $1,000 in it, and let's also suppose that T0 is the address that's holding the value of the balance of my account. And so I have two threads that are executing basically a sequence of 3 instructions. So what do they look like? The first thing is I load 0t0 into t1. So that means get the value that's at t0, which is holding the address of where I'm storing my balance. And so it's getting the balance and putting into this temporary register t1. I then decrement by a1, which is the amount that I want to take out of my account. And so I decrement t1 by a1, and then I store that t1 back into the same memory location, okay? So if I had $1,000, I take $50 out, my balance is now $950. Now my second thread comes along, it reads the balance, it sees that it's $950, takes $50 out, drops it to $900, all is good, right? What can go wrong here? What happens if the execution of the instructions looks like this, right? What if they were interleaved? So now what happens? Okay, let's take a quick look. Well, when thread 1 reads the value of the balance of the account, it's going to read $1,000. Okay, but before it has a chance to update that value, thread 2 comes along and it reads the value and it also reads $1,000, right? Now they both decrement by 50, but what they end up both storing back into the account balance is just $950, okay? So what happened here? I took out $100, but I only decremented the balance of my account by 50, right? Clearly a problem here. So what this example shows is that sometimes you have what we call critical sections of the code, where it's imperative that all of those instructions occur together without being without any interleaving of another process running some other instructions. Okay, and so another name for this constraint is called mutual exclusion, and basically the solution to it is what we call atomicity, which is basically we have to have a mechanism for ensuring that executing those 3 instructions is as if I was executing a single instruction that does both the load, the update, and the store. Okay, so I need to be able to do all 3 of those operations without being interrupted. So how do I use semaphores in order to do this? So what is the precedence constraint that, exists here? Basically what I'm saying is that either thread 1 has to go first, or let's say thread A has to go before B, or thread B has to go before A. I don't care which one goes first, but I need to make sure that an entire thread runs before the other one's going to run. Okay, so how can I deal with that with semaphores? What I'm going to do is I'm going to define another semaphore. Let's call it a lock in this case. And in this case, I'm going to initialize my lock to 1. Okay, this is what we call a binary semaphore. Okay, so what it's indicating is this value locked or not? And so then what I can do is I can wrap my critical section with a receiving of this lock and then freeing up this lock. And so it looks something like this, where before I touch the balance and update it, I'm going to wait to get this lock. Once I've gotten the lock, that means that only one thread has access to this bank account balance. Okay, so it does what it needs to do to it, and then when it's done, it signals the lock. Okay, and so because I initialize this lock to 1, only one of these threads is going to be able to modify, to look and modify the account balance at any point in time. So now we get into kind of, this complicated question, which is, what's the granularity of this lock that makes sense, right? So suppose like that I have, Bank of America, and it only supports a single lock for the entire bank, right? Would this work well? No, right? Why doesn't it work well? Yep.
Because if a lot of people want to access the bank accounts at once, they'll have to wait for other people to finish before they can start their own transactions.
Exactly, right? So that's, too coarse of a grain, right? But suppose that instead, my lock, I had a different lock for every single account. Would that work? It would work in the sense that, two accounts that are independent of each other wouldn't have to wait on each other. But, that the resources required to support that might be too great, right? And so typically what happens is we do some kind of intermediate granularity where we might say, all accounts that end in 004 get one lock, and all accounts that end in 005 get another lock, and so on, okay? And so the key point to take away here is that we're basically deciding what this lock means, okay? So if we use the lock correctly, then it's going to help us solve this mutual exclusion problem. But if we don't, then it's not, or it might introduce yet another set of problems, which we'll see at the end of today's lecture. Okay. So now we can go back to our producer-consumer problem and think about, well, what is the problem if instead of having a single producer and a single consumer, I now have two producers and one consumer, okay? So here, P1 shows producer 1, P2 shows producer 2, and what we see is that the instructions are interleaved, okay? So what happens here is that both producer 1 and producer 2 are reading the same value of in. So what is producer 2 doing? It's basically overwriting the buffer at location in. It's getting rid of the value that producer 1 produced, okay? Clearly not the behavior that we want. So how are we going to solve this? With mutual exclusion semaphores, right? So we're going to add yet another semaphore to our piece of code here. Here we have a mutual exclusion semaphore. So we have a lock. It's a binary semaphore. So we're setting it to 1 initially to make sure that only one of our threads can actually run at any point in time. And so what we do is we wrap this critical piece of code, which is the part that reads the buffer and then increments the pointer to point to the next location within this lock. So basically we wait for a lock, we do everything that we have to do with this point related to this pointer in, and then we signal a lock. And similarly on the consumer side, we do the same thing with the out pointer, okay? So now, do we believe that this code will run properly and deal with all the precedence constraints and multiple producers and consumers? What do we think? It will. You might be a little afraid to say that at this point, but all is good at this point, okay? So what have we seen? We've seen that semaphores are really very powerful, right? With a single data type, we've been able to enforce a number of different things, right? We enforced 2 different kinds of precedence constraints. One was that said, don't consume something before it's produced. Another one that dealt with resource allocation, which made sure that I don't overfill my buffer, meaning I can't get more than n ahead of my consumer. And then we also use the same data structure for mutual exclusion in order to deal with this critical section that has to happen without any interruptions. Okay, good. So far this is looking pretty good and it's not too complicated, but now you have to ask yourself the question of how do we actually go about implementing semaphores? So we saw that a semaphore itself is a piece of shared memory, right? And the wait and signal instructions, they are going to basically do the sequence of read, modify, write that better not be interrupted, right? So how am I going to essentially treat, this read, modify, write as a critical section when I'm just trying to implement semaphores in the first place. So kind of a chicken and egg problem, right? So there are actually two approaches to dealing with this. The first, which is the most common solution, is that our ISAs support actually some atomic instructions, okay? So it has special hardware support to ensure that there are certain instructions that can do things like, you know, test and set a value, or read, modify, and write, all as if it was a single instruction, okay? So nothing can interrupt the sequence of events that you're trying to execute. And in fact, if you look at the RISC-V ISA, it also has a number of different atomic instructions that are available for your use. I've listed, you know, one here, but there are actually a few simpler examples as well. But the key is just that, you know, the most common solution to dealing with this is to actually have the instruction set architecture support special atomic instructions. Now, one other alternative, which is how things probably used to be done, is to use the operating system, right? And so we said that when we go into kernel mode, if we have an uninterruptible kernel, right, then what we can do is we could have implemented the signal and wait as a system call. So if I implement it as a system call, then it's basically handled by the kernel, which can't be interrupted, and so by definition, I'm treating it as a critical section. So that's another way of dealing with it, but as I mentioned, the more common is the ISA approach. All right, so let's think all about, you know, what can still go wrong, you know, when we try to, oh, yeah?
So I was just going to say, like, if you guys are interested in also like more of the thinking behind that decision-making process, if you download and read, or like you can download a copy of the RISC-V ISA. It's not terribly long, but throughout there's like notes where the architects explained all of their reasoning and all of their decisions. So like there's a little section, like half a page long, that says why they chose load reserve store conditional. It's pretty cool.
Although I will say it's not an easy read. Anyways, so back to what can go wrong, right? So suppose that, you know, I wanted to write a transfer function which allows me to transfer money from one account into another account, okay? Now, you know, I have two resources that I have to be careful with. I have to, you know, protect my source account, and I have to protect my destination account. Okay, so what am I going to do? I'm going to, you know, ask to lock both of those accounts. So now, you know, suppose that I have two users, and one of them is trying to transfer, you know, for $50 from account A to account B, and the other one is trying to transfer $50 from account B to account A. And just to, you know, be precise in this example, let's say, you know, account A is 6031 and account B is 6004, okay? So what can happen here? Well, remember now I need to acquire two locks. So imagine that the way that I wrote my transfer function was that I ask first to get the lock for account 1, and then I ask to get the lock for account 2, and then I do, you know, the transfer operations, and then I free those two locks. Well, let's take a look at what would happen here. If we look at this example, well, you see that the first guy has 6031 as account 1, and the second one has 6004 as account 1. So if the instructions happen to be executed in an interleaved manner, where first I grab the account 1 lock for thread 1, so it grabs 6031, then I grab the account 1 lock for thread 2, so it grabs, you know, 6004, and now thread 1 comes back and it wants to grab the second lock. Well, the second lock isn't available because thread 2 just grabbed it. And it's not going to become available because thread 2 is stuck there not being able to make progress. Okay? Similarly, in thread 2, it can't grab its second account for the exact same reason. So what happens? Nobody makes progress. Okay? So this is what we call the dark side of synchronization, which is that if you're not careful about how you use synchronization, you can get yourself into a lot of trouble, and you can actually get into what we call deadlock situations where nobody can make any forward progress. So before I tell you how to deal with this, I'm just going to tell you about another very well-known problem that illustrates this deadlocking problem. And this is known as the dining philosophers problem. And the way this problem is stated is as follows. Suppose that you have n philosophers sitting around a table, and you have n chopsticks for them to use, and you put these chopsticks, one chopstick between each pair of philosophers, as shown in this picture. Okay? Now these philosophers follow a very precise algorithm of how they go about eating, and their algorithm says, first I'm going to grab my left chopstick, then I'm going to grab my right chopstick, and then I'm going to eat. And then when I'm done, I'm going to put both of my chopsticks down. Well, if you think about it a little bit, does anybody see a problem here? Yes, right? They're all going to, grab their left chopstick, but now not be able to grab their right chopstick, so none of them can make progress. Okay? So what are the conditions that led to this deadlock problem? There's a bunch of different issues here. So let's just go through them quickly one by one. So the first is mutual exclusion, right? So only one thread can hold a resource at a given time. Right? So once somebody grabbed this left chopstick, it's not available for the other guy to grab it, and so that's going to lead to an issue. The second problem is what we call hold and wait, which is once I've grabbed a resource, I don't let go of it. Right? So even if I can't make forward progress, I'm still holding that resource, and I'm not making it available to anybody else. The next issue is what we call preemption. So there are systems where, somebody higher up, or you have some kind of priority between processes, so the one with a higher priority would ultimately win in this kind of situation. But in this simple example, we don't have any preemption as well. And the last thing is that we have a circular wait situation, where they're all basically, stuck waiting on each other, and none of them can make progress. So how do we deal with this? So there's two solutions. One is avoidance, and another is to basically have a way of detecting that you're going to get into deadlock and recover from it. So for this particular example, one solution that works is the following. Suppose that instead of saying that the way that the philosophers are going to eat is by grabbing the left chopstick and then grabbing the right chopstick, instead let me, number each one of my n chopsticks, okay? And now the algorithm that they should use is the following. First, they have to grab the low-numbered chopstick. Then they grab the high-numbered chopstick. Then, if they have both chopsticks, they eat, and then they put the chopsticks down. So, if they follow this algorithm, can you end up in a deadlock situation? Any guesses? So you can't, right? Because the philosopher that grabbed the chopstick with the highest index is guaranteed to have first grabbed a chopstick with a lower index. And so at least that philosopher is going to be able to eat, make progress, and then return its chopsticks so that then some other philosopher can move forward, okay? And so basically by being much more careful about how we do the synchronization, we can avoid deadlock. Okay, so now back to our bank account problem, where we want to transfer money from one account to another. How could we apply this, same concept in order to avoid deadlock in this situation? Any ideas? How about this? Suppose I took the minimum of the account numbers and I called that A, and I took the maximum of the account numbers and I called that B, and in both cases I always wait for lock A before I wait for lock B. So what's going to happen now? In both situations, whether my account 1 is 6031 or my account 1 is 6004, both of them are first going to be waiting for lock A, which is the minimum of the two, okay? And so they'll both first be waiting for 6004, which means that nobody is going to grab 6031, so whichever one of the two is able to first grab that 6004, it's also then going to be able to grab 6031 and be able to proceed, okay? So in this manner, we've resolved the deadlock problem. Okay? And so this slide here is just a summary of the concepts that we went through. And so basically, as soon as we deal with communication among parallel processes, we need to worry about synchronization. We solve synchronization problems using our semaphores, which deal with things like precedence constraints, as well as dealing with critical sections. We do have to be very careful about how we do our synchronization so that we don't end in a deadlock situation. Any questions? Great. That's it for today. Thank you.